January 14th, 1945, 3:27 a.m., somewhere west of the Oder River. The night is black enough to swallow entire armies. Frost clings to the hulls of German Panther tanks lined beneath a tree line, engines silent, crews holding their breath as they wait for the order to advance. Above them, the sky pulses with distant flashes, Allied bombers hunting for armor concentrations before dawn. Inside a cramped Allied radar trailer nearly 40 kilometers away, the operators lean closer to their screens. Moments earlier, clear metallic reflections appeared along the riverbank, textbook signatures of a German armored column. Dozens of tanks, a perfect target. Then, without warning, the echoes weaken. The shapes blur. And in less than a minute, the tanks vanish from the radar entirely. The operators think it's a malfunction, a loose cable, a failing vacuum tube. They run diagnostics, recalibrate, sweep again, nothing. But the tanks are still there, engines warm, crews ready, steel giants preparing to surge toward the front, invisible not to the eye, but to the machines designed to expose them. To understand how German armor disappeared from Allied radar that night and how one engineer's forbidden idea made it possible, we must go back to the beginning. By late 1942, a new kind of warfare was tightening around the German army, one they could neither outrun nor overpower. Radar, once an experimental technology used mainly for coastal defense and night-fighting aircraft, was becoming the Allies' most reliable method of locating enemy movements, and tanks with their broad metallic plates and powerful engines were among the easiest objects for radar to detect. Across the Eastern Front, British and American reconnaissance aircraft equipped with ASV and ground mapping radar systems began sweeping vast areas with unprecedented precision. Even in darkness, cloud cover, or heavy forest, German armor could be tracked long before it reached the battlefield. Columns that once moved safely at night were now traced across icy plains by operators who never saw the tanks with their eyes, only the pulsing echoes on phosphor screens. The Wehrmacht quickly realized it was trapped in an unfolding technological crisis. The Luftwaffe was losing control of the skies. Air reconnaissance flights were becoming harder to intercept. And the Allies were learning to combine radar intelligence with bomber strikes and artillery barrages. The result was devastating. Tanks destroyed before they fired a shot, ambushes neutralized before they were set, and armored reinforcements caught on the move. By 1943, German commanders reported a disturbing pattern. Allied attacks were arriving not by chance, but with uncanny timing. Armor regrouping points were struck precisely when the tanks were most vulnerable. Supply convoys were intercepted at night. Strategic redeployments became deadly risks. The fear spread through the ranks, even when hidden from aircraft. They were no longer hidden from the machines guiding them. Attempts to counter this new threat fell short. Camouflage nets worked against the eye, not against electromagnetic waves. Smoke screens dispersed too quickly. Terrain masking helped, but only in a few regions. Radar saw right through deception that once defined blitzkrieg. And as Allied radar technology improved month after month, German units found themselves facing an impossible situation, one where movement meant exposure and exposure meant destruction. But the real crisis began when the Allies introduced their next generation of radar systems. Devices that could detect tanks from even greater distances with higher clarity and under almost any conditions. A shift that made one thing unmistakably clear. If the Germans could not hide their tanks from radar, they would lose them long before they reached the battlefield. By early 1944, the situation reached a breaking point. Allied engineers unveiled a new generation of radar systems, H-2S Mark III, ASV Mark VI, and advanced ground-based sets positioned along key front sectors. these devices no longer relied solely on detecting large, clean metallic returns. They used shorter wavelengths, more refined pulse patterns, and improved signal processing. The result was a technological leap the German army had not anticipated. Now, radar could identify armored formations even in dense forest canopies, where visual reconnaissance was useless. It could map the outlines of tanks dug into defensive positions. It could track columns through heavy snowfall, a condition once believed to offer perfect concealment. And in some cases, radar-equipped aircraft could sweep entire regions in minutes, relaying real-time data that matched artillery targeting grids. Suddenly, German tank units were being located before they even left their staging areas. At the same time, the Luftwaffe's decline accelerated. With fewer aircraft available to contest Allied reconnaissance operations, the Allies conducted radar-guided sweeps with near impunity. British Mosquitoes and American B-24s equipped with ground mapping sets scanned roads, rail lines, and armored regrouping points day and night. Even small armored detachments showed up as unmistakable blips, large, hard-edged reflections that radar operators learned to recognize instantly. In headquarters across the eastern and western fronts, German generals reviewed radar intercept reports with growing alarm. Their greatest battlefield asset, mobile armored power, was turning into a giant, track-driven liability. In desperation, countermeasures teams experimented with every conventional form of camouflage: tarps, netting, frozen mud coatings, vehicle spacing tricks, dummy tanks. Nothing fooled radar for long. The technical truth was unavoidable. Radar did not care about color, foliage, or clever positioning. It only cared about the electromagnetic reflections bouncing off metal. The Wehrmacht needed a solution that didn't exist, and yet beneath the frustration and hopelessness, one quiet engineer had already begun exploring something radically different, something that didn't attempt to hide tanks from the human eye, but from the invisible waves sweeping over Europe. A solution no one believed was possible, a solution almost no one wanted to hear. His name rarely appears in official reports, not because he was unimportant, but because his work, his experiments, and his failures were buried inside the quiet, overlooked workshops of Germany's late-war research industry. To most of the officers who passed him in factory corridors, he was simply the chemist, a thin, bespectacled engineer with dark hair, ink-stained fingers, and a habit of staring too long at the surface of machines as if he were listening to them. But to those who worked beside him, he was something far more unusual, a man who believed materials could reshape the physics of the battlefield. His name was Dr. Ernst Keller. Born in 1907 near Stuttgart, Keller grew up in a family of machinists. His father built tools, his older brother repaired radios. Ernst spent his childhood grinding powders, mixing pigments, and examining how metals reacted under heat. It was a simple curiosity then, but it would shape the most controversial idea of his adult life. By the late 1930s, Keller had become a specialist in surface coatings and electromagnetic absorption, an obscure field combining chemistry, physics, and electrical engineering. He had worked on radio housings, submarine components, even coatings for early radar testing equipment. He wasn't a soldier, he wasn't a weapons designer. He was a quiet academic who believed that materials could solve military problems others had never considered. When war erupted, Keller found himself reassigned to a military research group supplying paints, anti-corrosion treatments, primers, and protective coatings for tanks, half-tracks, and artillery pieces. It was unglamorous work. Most engineers around him fought for positions in high-profile weapons projects, rockets, aircraft, optics. Keller mixed compounds in metal trays and tested how long they lasted under mud, snow, and engine heat. But he listened. He listened to tank crews complaining about being hunted at night. He listened to radar operators explaining how easily metal betrayed its presence. And he listened to commanders frustrated by the enemy's growing ability to spot armored units from miles away. While others blamed pilots or poor concealment, Keller blamed something much more fundamental: the physics of metal reflecting electromagnetic waves. By 1943, he had become obsessed with a question that seemed ridiculous at the time. What if a tank could absorb radar waves instead of reflecting them? The idea didn't come out of nowhere. Keller had studied early electromagnetic absorbing materials used in laboratory equipment. He had experimented with ferrites in the late 1930s. He understood how certain carbon structures and iron-based compounds interacted with radio frequencies, but applying these principles to a tank, a 45-ton steel vehicle, was something entirely different. It sounded like a fantasy, as a misunderstanding of radar itself. His colleagues dismissed the notion instantly. Radar wasn't fooled by color, it wasn't fooled by paint. It read reflections, not surfaces. Keller's supervisors told him to focus on corrosion resistance. But as Allied radar sweeps intensified, as German tank movements became predictable targets, and as radar-guided strikes destroyed entire armored companies in motion, Keller's fascination hardened into something far stronger. A conviction that the answer wasn't in hiding tanks from the eye, but from the wave. He began to fill notebooks with sketches of coated surfaces, layered compounds, and powdered mixtures that reacted differently across the microwave and metric wavelengths the Allies used. He wrote calculations no one asked him to make. He proposed tests no one approved. He worked late, long after the other engineers left the workshop, mixing tiny batches of blackened compounds whose purpose he kept to himself. To the rest of his unit, Keller was becoming a nuisance, an academic, drifting into impossible theory while frontline tank crews were dying. To Keller, the others were blind to a problem that was about to reshape the war. And as he pushed deeper into his quiet, unofficial experiments, he knew one thing with absolute clarity: if he ever proposed his true idea out loud, he would be laughed out of the room, but the idea forming in his mind would be dismissed before he could even finish the sentence. In the winter of 1943, Dr. Ernst Keller's workshop felt more like a forgotten corner of the war than an official research facility. The walls were stained with old paint tests. The air smelled of solvents, rust, and coal dust. A single overhead lamp buzzed faintly, casting long shadows across piles of metal plates, mixing bowls, and improvised heating elements. This isolation suited Keller. If anyone had been watching closely, they would have wondered why he was ordering unusual materials: ferrite powders, magnetite, finely milled carbon, and binders not normally used in military coatings. But Keller filed every request under vague technical justifications: thermal protection, corrosion inhibitors, experimental base layer. During wartime shortages, such explanations were often accepted without deeper inspection. His small team had long since learned to ignore his late-night experiments. They focused on delivering coatings that actually mattered: anti-rust formulas, primer adhesion improvements, weather-resistant pigments. Practical things, real things. Keller, meanwhile, kept returning to one impossible question: how do you make a 45-ton steel machine behave as though it isn't there? He ran early tests on scrap metal plates. The results were underwhelming. Some mixtures cracked when exposed to heat. Others peeled under vibration. And many simply did nothing at all. The radar reflections remained unchanged, bouncing off the metal surface as if mocking his effort. But Keller knew failure was part of physics. The properties he needed, absorption, attenuation, scattering disruption, demanded a delicate balance. Ferrites could absorb some radar frequencies. Carbon could dissipate electromagnetic energy as heat, but combining them into a paintable, durable coating, That was another challenge entirely. He adjusted particle sizes, mixing ratios, and layer thicknesses. He changed binders, heated mixtures, cooled them, textured the surfaces, applied coatings at angles, tested multiple layers. He tried low-frequency absorption, then focused on the shorter wavelengths used by Allied airborne radar. He failed dozens of times, but each failure was precise. Each one taught him something new. Keller wasn't driven by medals or recognition. He rarely thought about his own safety. What he thought about, quietly, privately, were the tank crews who never came home. The ones who burned inside their Panthers and Panzer IVs after being located by radar long before the enemy saw them visually. Young men who had no idea they were being hunted by unseen waves. To Keller, science wasn't abstract, it was human, and radar was killing men who couldn't see the threat coming. One evening, a commander visited the workshop, furious that Keller had delayed a delivery of standard paint batches. The officer accused him of wasting resources, wasting time, even undermining the war effort. Keller said nothing. He simply apologized and resumed the mandated tasks, waiting until the officer left before returning to his experiments. His colleagues pulled him aside afterward, urging him to drop his fantasy coating idea and focus on surviving the war. Some genuinely worried for him. The High Command had little patience for eccentricity by 1944. Others mocked him openly. One engineer joked that Keller might as well invent invisible steel next. Keller didn't argue, he never did. He simply returned to his small table, to the powders and compounds slowly filling the margins of his notebooks. His hands were cracked from handling solvents, his eyes burned from sleepless nights, but his conviction only deepened. Because while everyone else was trying to hide tanks from the sky, Keller believed the answer was to erase their electromagnetic shadow. Piece by piece, mixture by mixture, he was getting closer. And yet, buried inside his notebooks was a formula no one wanted to hear, a formula he still had not dared to present to anyone, a formula that would soon force him to confront every skeptic, every superior, every voice telling him it couldn't be done, because the war was about to reach a point where even the impossible had to be considered. The meeting that would change everything took place in a cramped conference room lined with outdated charts and peeling wall maps. A handful of officers and engineers gathered to discuss countermeasures against Allied radar. Most arrived expecting the same discussion as always: nets, terrain masking, false positions, decoys. Nothing revolutionary, nothing risky. Dr. Ernst Keller stood quietly near the back, clutching a small folder of handwritten formulas and test results. He hadn't been invited to speak. He wasn't on the agenda. But desperation had made the atmosphere unusually open to suggestions. Commanders needed something, anything, that could slow the relentless accuracy of Allied reconnaissance. Halfway through the meeting, after listening to proposals that had already failed a dozen times, Keller finally stepped forward. He cleared his throat. "I believe," he began cautiously, "that radar detection can be reduced using an electromagnetic absorbing coating." Silence settled over the room like dust. One officer raised an eyebrow, another chuckled. The senior engineer in charge looked as though Keller had proposed turning tanks invisible with mirrors. "Paint," someone muttered. "Radar doesn't care about color," another snapped. A third voice added, "This isn't children's camouflage, Keller." He tried to explain, not color, not deception, but physics, radar waves interacting with ferrites, electromagnetic energy converted to heat, carbon structures disrupting reflection patterns, surface texturing that scattered wave returns instead of sending them back intact. But the room refused to follow him. The idea sounded absurd. Radar saw metal. Metal was metal. And the notion that a thin coating could alter the electromagnetic signature of a 45-ton tank seemed like delusion. Worse, Keller's proposal was politically dangerous. High command despised experimental distractions. Any project that required new materials, new production lines, or new logistics was viewed with suspicion. The senior engineer cut him off with a wave of the hand. "This is not the time for fantasies. Paint cannot defeat radar." A few men laughed quietly. The proposal was dismissed before Keller had finished explaining it. His folder remained unopened on the table, untouched, ignored. And yet, as he gathered his papers, cheeks burning with humiliation, one thought refused to leave him. They were wrong, and he could prove it. Still, he wasn't ready to let the idea die. Keller returned to his workshop with the same folder of rejected notes pressed tightly under his arm. But instead of feeling defeated, he felt something sharper, a kind of cold certainty. If no one would listen to him, then he would simply have to prove it without their permission. He began by preparing small metal plates, each one sanded to identical texture. Onto these, he applied carefully measured mixtures of ferrit powder, carbon black, and binders blended into an inky, matte coating. He heated them, cooled them, flexed them, subjected them to vibration tests, anything to simulate the harsh environment a tank endured on the field. Most mixtures failed almost immediately. Some flaked off under heat. Others absorbed moisture and softened. A few reacted chemically with the primer beneath them, producing a brittle, ash-like surface that crumbled under pressure. One disastrous batch even corroded the steel plate it was supposed to protect. But Keller documented every mistake, every crack, every blister, every unexpected result. Then slowly, quietly, the failures began to reveal patterns. Certain ferrit-to-carbon ratios improved low-frequency absorption. Some binders held up better against engine warmth. A textured application created tiny surface irregularities that scattered radar waves, weakening their return strength. And when Keller combined 3 of these promising characteristics, he noticed something different during a basic lab test. The radar reflectivity dropped, not by much, but conclusively. He repeated the experiment, and again. Each time, the coated plate produced weaker radar echoes than the uncoated control sample. It wasn't invisibility, it wasn't perfection, but it was absorption, real absorption. Word leaked to a junior officer who occasionally visited the workshop. Curious, he watched Keller's test and frowned, not in disbelief, but in recognition. "If this works on a plate," he said quietly, "could it work on a tank?" Keller didn't answer immediately because he wasn't sure, not yet. The mixture was still fragile, still experimental. A tank's armor vibrated, flexed, and heated in ways laboratory plates never did. And Allied radar grew more sensitive by the month. But the possibility was real. And just as he prepared to refine the mixture into a formula worthy of a field test, disaster struck across the front. Radar-guided Allied strikes destroyed an armored battalion moving at night, a night they believed was safe. Suddenly, Keller's theory was no longer a curiosity. It was an emergency. And just as the formula began to work, the war situation collapsed around him. By the autumn of 1944, the German army was fighting a war it no longer controlled. Every movement of armor, every redeployment, every attempt to reinforce a collapsing line risked exposure to Allied radar sweeps that now reached deeper than ever before. British and American aircraft equipped with the latest H-2S and ASV radar systems circled silently above the front, mapping roads, forests, and open fields with pulse patterns that could detect a tank column long before dawn. Ground-based units along the Western Front fed constant radar updates to artillery and bomber groups. To the soldiers on the ground, it felt like there was no darkness left in Europe. 2 disastrous incidents accelerated the crisis. First, an armored regiment near Aachen was struck by a precision bombing run only hours after repositioning under night cover, a move they believed had gone unnoticed. Then, in East Prussia, a Panther detachment was annihilated by radar-guided artillery despite being hidden beneath dense pine canopy. Tank crews began to whisper, "They can see us even in the forest." Commanders complained to Berlin, demanding something anything to help armour move unseen, but there was no miracle solution, not one the High Command believed in anyway. Then came a turning point. A research liaison officer reviewing scattered R&D reports found Keller's abandoned proposal. He scanned the handwritten notes, saw the reflectivity tests, and immediately recognized the significance. A week later, Keller received an unexpected message. He was ordered to present his coating experiments to a field evaluation team. The timing could not have been more critical. Allied forces were preparing for a new offensive, radar sweeps growing heavier each night. German intelligence warned that another armoured concentration had already been detected and targeted. Keller understood the meaning instantly. This wasn't an opportunity. It was desperation. He was given exactly one chance to show whether his strange mixture could save tanks from the machines hunting them. And as the orders unfolded, he learned the final detail. He would not be testing his mixture on metal plates this time. He would be applying it to real tanks under combat pressure, with almost no preparation time. The orders were delivered with urgency and little explanation. Keller was to travel to a forward maintenance depot near Küstrin, where a small armoured detachment waited for last-minute preparation before deployment. These tanks, mainly Panthers and Panzersorvies, were expected to participate in a counter-attack within days. Allied radar aircraft were already scanning the region relentlessly, and several German movements had been spotted and targeted the previous week. Keller's assignment was simple in words, impossible in reality. Apply his experimental radar-absorbing coating to a select group of Tang, and pray it worked. When he arrived, the scene was chaotic. Mechanics rushed between vehicles, supply trucks sputtered, overloaded, and late. Orders changed hour by hour as commanders reacted to new radar intercepts showing Allied sweeps edging closer. The constant hum of distant engines overhead reminded everyone that radar-equipped aircraft were somewhere in the sky, even if unseen. Keller set up a makeshift workstation beside a Panther, whose crew stared doubtfully at the buckets of thick, black mixture he began preparing. They had no idea what he was doing, and he wasn't sure he could explain it in a way anyone would accept. The problems began immediately. There wasn't enough ferret powder to coat all tanks evenly. The binder he relied on was reacting poorly in the cold. Worse, the depot lacked proper drying equipment, meaning each coat would cure slowly and imperfectly. Only 6 tanks could be treated at all, and even those would receive hasty, uneven layers Keller had never tested under realistic battlefield conditions. The crews complained that the black coating ruined their camouflage. Keller countered that color didn't matter, not against radar. The men looked unconvinced, but orders were orders. As night fell, the temperature dropped further, slowing the curing process to a crawl. Keller worked with numb fingers, applying the mixture as evenly as possible, though he knew many areas remained thin or incomplete. One tank received barely half a coat before the supply of binder ran out entirely. Meanwhile, new intelligence arrived. Allied radar sweeps had intensified. A major operation seemed imminent. Recon aircraft were already patrolling the sector. The depot commander informed Keller that the tanks would move before dawn, ready or not, and then, as the final hour approached, everything that could go wrong began to go wrong. The night before the tanks were scheduled to move, the maintenance depot felt like a machine coming apart. Engines coughed in the cold, orders changed faster than they could be written down. and Keller, exhausted and hunched over a half-empty bucket of experimental coating, watched his carefully calculated formulas dissolve into chaos. The problems began with the first Panther. A large patch of the coating, still uncured from the freezing air, began to crack along the turret's curve as mechanics tested the traverse gear. The cold had stiffened the mixture faster than expected, turning one layer brittle. As the turret rotated, long spiderweb fractures streaked across the surface. The loader swore. The commander shook his head. Keller felt his stomach tighten. They tried to repair the damage, but the patchwork dried unevenly, leaving glossy and matte areas Keller had never tested together. A second tank fared even worse. The binder failed entirely along the engine plate, and entire sections of the coating peeled off in curling sheets when the mechanics started the ignition test. By midnight, it was clear the coating wasn't curing uniformly. Some areas hardened too fast, others remained tacky. On the fourth tank, the mixture reacted with the old primer, leaving a chalky residue Keller had never seen before. The men began to mutter, wasting time. Sorcerer's paint. Just slows us down. Won't fool anyone. Keller kept working. He reheated mixtures with a portable lamp. He thickened some batches, thinned others, hoping the last-minute adjustments would stabilize the surface. He wrapped some areas in cloth strips to protect the coating as it cured. He textured other sections with improvised tools to increase their irregularity, but nothing he did was controlled anymore. Every fix created a new unknown. Then came the news Keller feared most. At 02:15, a runner arrived at the depot. Allied radar intercepts showed multiple sweeps across their sector in the last hour. Worse, one aircraft was mapping the region on a fixed pattern, the same kind used before previous bombing raids. If the column was detected now, the tanks would be struck before sunrise. The depot commander pressed Keller, "Will this work or not?" Keller couldn't answer, not honestly. His tests were meant for laboratory setup, not frozen tank hulls coated in 3 different mixtures under combat conditions. The formula needed time, controlled curing, precise layering, none of which he'd been given. And then the situation deteriorated further. At 03:04, a Panther test fired its engine. The resulting vibration shook loose a large drying patch on the glacis plate. The coating slid down the armor in thick, black streaks, pooling beneath the tank like spilled oil. The crew erupted in frustration. Minutes later, a second tank suffered a different issue. Heat from the engine warmed the rear plate too quickly, causing the uncured mixture to blister. Small bubbles formed, expanded and burst open, leaving pitted craters across the surface. Keller felt the crisis closing around him. This wasn't a controlled experiment anymore. This was failure unfolding in real time. Then, as if timed to break the last thread of confidence, the air raid sirens wailed in the far distance. The men froze. In the sky, only darkness, but the sound itself told them everything. Allied aircraft were in the vicinity. Radar sweeps had found something, and the next step after detection was bombardment. The crews scrambled, preparing to move the tanks deeper into the forest. Engines roared to life. The vibration shook Keller's fragile coatings further. Chipped edges broke, several spots peeled. One of the 6 tanks ended up with less than 40% of the mixture intact, a far cry from Keller's intended coverage. The commander approached, voice tight. "We move now. If the enemy spotted us, we won't survive daylight." Keller watched the 6 partially coated tanks rumble forward, some streaked with cracks, some scarred with blisters, one nearly bare in places. This wasn't the formula he envisioned. This wasn't the breakthrough he had prepared for. This was a last-minute, flawed test under the worst conditions imaginable. The tanks disappeared into the tree line. Moments later, inside an Allied radar aircraft circling miles away, the operator noted something disturbing on his screen. A cluster of metallic echoes, previously detected, suddenly weakened. He adjusted the gain, recalibrated the sweep, checked the frequency. The echoes blurred, then grew faint. Something was wrong, and then without explanation, the signatures vanished entirely. At 03:27 a.m. aboard an RAF radar reconnaissance aircraft sweeping the Oder region, the operator stared at his display in disbelief. Moments earlier, the radar showed a clear, armored formation, large, high reflectivity signatures moving in a staggered column. Textbook tank echoes, predictable, trackable. Then the signals weakened, flickered, and faded into the background noise. The operator tapped the glass, adjusted the gain, reset the sweep. Still nothing. To him, it looked like a systems failure. To the officer beside him, it looked worse, a possible German jamming device. But the frequencies were clean. The noise floor was normal. There was no interference. The tanks had simply disappeared from radar. What Keller had spent months refining in secrecy was now revealing itself on a frozen battlefield. The principle was simple in theory, radical in practice. Prevent radar waves from bouncing back. Traditional tank armor reflected pulses like a mirror. Radar would emit a wave. The wave struck steel. The steel returned a strong echo. Operators saw clean, unmistakable shapes. But Keller's mixture, imperfectly applied, uneven, still curing, changed the rules. Inside the coating, ferrite particles absorbed electromagnetic energy, converting part of the radar wave into tiny amounts of heat. The carbon structures dispersed energy along the surface, scattering the pulse instead of returning it intact. And the rough textured application, originally a flaw, actually helped break up the radar reflection even further. The result wasn't invisibility, not true stealth, but enough absorption and scattering to push the tank's signals below the detection threshold of the Allied radar in use that night. In the forest, the German tank crews had no idea what was happening in the sky above. They only knew one thing: no bombs fell, no flares dropped, no artillery brackets landed around them. For the first time in months, their night movement remained unchallenged. Keller, riding in a truck behind the column, kept glancing upward, expecting the faint drone of bombers closing in. But the forest stayed quiet. Only the distant rumble of engines muffled by snow marked the tank's passage. Minutes stretched into half an hour into an hour, still no attack. At Allied Air Command, confusion spread. Radar contact had been lost. Attempts to reacquire the signatures failed. No metallic echoes, no movement trails, nothing to justify a strike. To them, the battlefield hadn't emptied. It had gone blind. Back on the ground, Keller stepped out as the tanks halted at their new staging point. Frost clung to the uneven black coatings. Some areas were chipped, others still tacky. One Panther's turret bore a patchwork of textures resembling burnt tar. It looked nothing like the elegant uniform surface Keller had envisioned. If anything, it looked like a rushed repair job rather than a revolutionary material. But the results spoke for themselves. The depot commander approached quietly, not triumphant, not convinced, yet undeniably shaken by what had just occurred. "No air attack," he murmured, "not even a reconnaissance flare." Keller didn't reply. He was still processing the same realization the radar operator had reached miles away. The tanks had slipped through Allied detection because the radar never truly saw them. Even flawed, even rushed, even unevenly applied, the mixture had changed the tank's electromagnetic signature enough to erase the clean reflections radar operators relied upon. In later analysis, Allied technicians would speculate about jamming, equipment malfunction, atmospheric interference. They would revise procedures, recalibrate systems, retrain operators. None of it would explain the truth, because the truth sat silently on those dark, frost-covered tank hulls. A crude, improvised version of Keller's formula had worked. Not perfectly, not elegantly, but decisively. The column had passed through radar sweeps without detection. Dozens of tanks had survived a movement that should have resulted in an ambush or bombardment. A frontline sector remained intact because 6 coated tanks had become partially, then almost completely, electromagnetically silent. What happened next would push Keller's idea from a rejected fantasy to one of the most urgent research priorities remaining in Germany's dying war machine. At dawn, the 6 coated tanks rolled into their temporary staging area, cold, mud-streaked, their blackened surfaces scarred from rushed application and freezing night air. They looked nothing like the sleek, uniform prototypes Keller had imagined. And yet, they had accomplished something no German tank unit had managed in months. They moved through an area under active Allied radar surveillance without being detected. As word spread among the crews, disbelief gave way to quiet awe. One Panther commander, initially dismissive of the strange paint, ran his gloved hand across the rough surface and muttered, "If this saved my men, I don't care what it looks like." Keller remained silent, exhausted, barely able to stand after working through 2 nights with almost no sleep. The depot commander approached him with a mix of suspicion and gratitude. 6 tanks moved, he reported. 6 tanks arrived, unchallenged, no radar-guided strikes, no aircraft sent to intercept, nothing. He paused. In this sector, that hasn't happened in weeks. Within hours, the results began to ripple through command channels. A field intelligence officer filed a formal report noting the apparent inability of enemy radar to track the coated vehicles. Another officer included an addendum comparing radar logs from the previous night. Expected tank signatures had appeared briefly, then collapsed completely and could not be reacquired. A pattern emerged. The treated tanks had become radar ghosts. The practical consequences were immediate and measurable. Quantified results. 6 tanks successfully passed through a monitored sector with 0 radar detection. 0 Allied reconnaissance aircraft attempted intercept during the movement. No artillery units adjusted fire onto the column. 3 separate radar logs from Allied monitoring posts showed unexplained signal dropouts. An estimated 120-150 tank crewmen avoided bombardment that would likely have occurred under normal circumstances. The new staging position remained intact, allowing a 400-man armoured company to regroup safely. For a German army being hunted relentlessly by radar, the numbers were staggering, but the impact wasn't only tactical, it quickly became strategic. Within 24 hours, Keller was summoned to present his findings to a regional command board. This time, no one laughed. Officers studied the irregular coatings on the Panthers with intense interest, running their hands across the rough surfaces, tapping the plates with knuckles, measuring thickness, comparing textures. A major from an armoured division asked the only question that mattered. How quickly can this be replicated? Keller hesitated. The truthful answer was painful. His mixture required ferrites that were now in short supply. The curing process was unpredictable in winter conditions. Surface preparation needed more time than frontline units typically had. And, most importantly, the formula had worked accidentally in ways that he didn't fully control yet. But the officers didn't care about the obstacles. They cared that the Allied radar had failed. Rumours began moving faster than official reports. Some tank crews claimed the coating made them invisible to aircraft. Others insisted the Allies were terrified of a new German cloaking device. Engineers whispered terms like absorption coating and EM shadow reduction, even if they barely understood what Keller had achieved. For the first time, High Command recognized that radar was not an unstoppable force of nature. It could be fought, it could be countered, and perhaps, if Keller's formula was refined, it could be defeated. A rushed directive followed. Produce enough coating to treat an entire armored battalion. Keller was given a new workspace, more assistance, and limited priority access to ferrite stocks normally reserved for electronics manufacturing. The order was clear: recreate the effect intentionally, reliably, and at scale. But as he prepared to begin this next phase, Keller couldn't ignore a sobering truth. The war was collapsing. Supplies were running dry. Factories were being bombed. The front was shrinking every week. Even if his coating worked perfectly, it might be too late to change the course of the conflict. Still, as he watched those 6 battered tanks, coated in flawed, uneven layers that had nonetheless fooled Allied radar, Keller felt something he hadn't allowed himself in months. Hope. A fragile, uncertain hope, but hope nonetheless. Because for one night, against overwhelming odds, the impossible had happened. And he knew the next phase of the story was far from over. In the final months of the war, as the German front lines contracted and fuel shortages crippled armored operations, Keller's breakthrough struggled to escape the chaos consuming the Reich. Factories were being evacuated or destroyed, rail lines were severed, ferret shipments disappeared in transit. Sometimes entire batches of chemicals Keller needed simply never arrived. Yet despite the disorder, small pockets of progress emerged. A reduced, improvised production line managed to create enough coating for a few dozen tanks across 2 armored units. The applications were inconsistent. Some vehicles received full multi-layer treatments, others only hastily brushed on mixtures. But even this limited deployment produced scattered reports that echoed the results from Kustrin: radar detection failures, signal dropouts, unexplained gaps in Allied reconnaissance logs. In one documented case, an armored company relocated during the night without drawing the bomber sorties that had devastated their previous movement. In another, Allied analysts attributed the absence of expected tank signatures to weather interference, despite clear skies and normal atmospheric conditions. None of these incidents turned the tide of the war. None saved the collapsing German defensive lines, but each one confirmed the same quiet truth. Keller's idea had been real. After Germany's surrender in May 1945, Allied technical teams began sweeping through research facilities across the country. Among the papers, formulations, and scattered laboratory notes they collected were Keller's notebooks, water-stained, soot-darkened, filled with chemical ratios and radar reflectivity charts. The Allies were stunned. Buried in those pages were early calculations and material concepts that echoed what Western scientists would explore years later during the birth of radar stealth technology. While Keller had been limited by resources, by time, and by the collapsing infrastructure of a dying regime, the principles he identified were sound, absorption, attenuation, scattering, electromagnetic signature reduction. Decades later, engineers researching radar-absorbent materials for Cold War aircraft would unknowingly follow the same path Keller had traced with charcoal powder on the edge of a freezing battlefield. His work did not disappear. It was picked up, studied, expanded, refined, not by the country he served, but by the world that inherited the technology of a war increasingly shaped by invisible waves. As for Keller himself, his story ended far more quietly. Detained after the war, he was eventually released when Allied investigators determined he had never been part of ideological programs nor involved in inhumane experimentation. He was simply an engineer who had tried to solve a problem few others even understood. He lived out his life in relative obscurity, working for a civilian materials manufacturer, the chaos of the war years slowly fading into the private corners of his memory. He rarely spoke of his wartime research. To most who knew him, he was a reserved, methodical man who preferred silence to praise. But in his personal notebooks, never published, never widely examined, he left a single reflection on the project that had consumed him. A wave can betray what a man cannot see, and a surface, properly prepared, can make that wave blind. Today, historians and engineers studying early radar countermeasures occasionally stumble upon scattered notes or technical references hinting at the unusual coating tested in the war's final winter. They see traces of a concept far ahead of its time, underdeveloped, underfunded, but unmistakably visionary. And though the war was already lost by the time Keller's idea took form, the legacy of that rough, uneven coating lived on in ways he could never have imagined, because the world would eventually learn what he proved in one desperate night. Steel does not have to shine, metal does not have to reflect, machines do not have to be seen by the eyes of radar. But none of it would have happened without one man's stupid idea.